Вам все нормально. Okay, I'm about to start, but I need to make sure that you can see my slide and hear myself. Do you hear me?
Yes.
Okay, is everything okay? Shall we start?
Sure.
Can you? Yeah.
Sure.
Is everything?
Everything's okay. Everything's perfect. Okay.
Okay, good. So let's go. No, maybe let's wait for one more minute and then we'll start. Okay, let's start. So what are we going to discuss today? Two topics. The first topic is we'll talk about analytic functions of Nijenhuis operators, and the second that's a splitting theorem. So both items of my plan today, analytic functions and splitting theorems, they are, I would say, very important instruments in the Nijenhuis geometry. I would say two basic instruments. The plan of my lectures is as follows. Now, first, I will have to discuss what actually I mean by analytic function of an operator. Of course, we know what is a function of a matrix of an operator is, so everybody knows what is a polynomial of a matrix or what is exponent of a matrix. That's kind of clear, but I suggest to consider a little bit more general the functions which still make perfect sense, and we will see how it works. And then, why are we going to discuss this? Not just because next that I will explain that so if we have a Nijenhuis operator and apply a function, real analytic function to this operator, then the new operator we obtain is still a Nijenhuis operator. And we will see that in this way we can produce some very nice operators. So being just analytic functions, slightly unusual, you will see, so this leads us to very nice the results in Nijenhuis geometry. So next, we will be talking about splitting theorem. The splitting theorem has something to do with distributions and affiliations generated by Nijenhuis operations. So for this reason, first I will remind you some very general facts about distributions and Frobenius theorems on integrability of distribution. We'll talk about splitting theorem, which is in fact the splitting theorem in Nijenhuis geometry. This is no, I would say this is a very natural analog of the similar splitting theorem in Poisson geometry. Okay, so let's start. Analytic functions of operators or analytic function of the matrices. So what is that? What is the idea? That's why I want to talk about this. The idea is as follows. So if we know from the previous lecture, so the following fact. If we have a Nijenhuis operator and we consider a polynomial with constant coefficients, that's important, constant coefficients of this operator, then we will get a new operator, which is still Nijenhuis. And so I'm going to explain, I repeat, that instead of a function, instead of polynomial piece, we can consider any real analytic function. No, but now I need to explain that what is the function? What is the function I'm going to consider? Which functions are allowed and which are not? No, of course, the exponential function, so it's a perfect example of a matrix function. So everybody knows it, uses it. It goes without saying. Also, you can consider sine of a matrix or the hyperbolic sine and many other examples. Of course, you can do it. No, but we need something more general, and I will explain what we need. So here is a general construction. Of course, the matrix function corresponds to usual function. And so that's one point. And the other point, this function should be complex functions. What is the reason? Why we should consider complex functions? So the reason is that so it's even if you have a real matrix, it may happen that eigenvalues of this matrix are complex numbers. And for this reason, so we need somehow complex functions defined on complex plane, or maybe not on the whole plane, but a certain subset. And the first what we will do, we will define this subset. So the domain of my function will be a compact set K on the complex plane. Satisfying certain properties. So the first property is as follows. So this set K, this compact set, is not necessarily connected itself. What is important that the complement to it should be connected. So that's the first condition. So, and my function is defined on K. On K, this function is continuous, but in the interior of K, this function must be holomorphic. It must be very good, the very good complex function. Okay, that's there is another condition. Now, since I want to deal with real operators, so this domain K should respect this kind of property of function must be real value at the end of the day, and for this reason the K this domain must be symmetric with respect to the complex to the real axis. Sorry. So together with each z bar complex conjugate also belongs to K. Now, what about function? So my function, which I'm going to define, to introduce, so what is written here, basically, so this is to say that this function is somehow is obtained from a real function, let's say. So it respects, let's say, the real line. So in particular, if you restrict this function on the real line, then you will get real result, so real value. So f of z equals f bar of z bar, so some sort of symmetry. And finally, I'm interested in a function which is defined not on a complex domain, but on the matrices. So there should be some sort of this relationship between this function, this domain, and operators I'm going to consider. So the operators must satisfy the following property. The spectrum of operators I consider so it must be located in the interior of K, in the interior of the domain. I can consider just a set of operators, so satisfying this condition, or I consider, I may think of them, so these operators defined on our manifold. So we have a manifold, and so we have one tensors, and at each point X, the spectrum of L belongs to the interior of K. So let's assume that the properties are they're fulfilled. In particular, K could be just a very big ball, for instance. But not only. Let me give you some. I will try to draw some examples of K. So I have this is complex domain, so it's complex plane. So this is C, and so what I can do, I can take, for example, so this part of the complex plane as K, or so I can do it. I can take some piece in the upper half plane, and of course then that I will have to consider symmetric piece so downstairs in the lower half plane. So that's another good example of K. Okay, good. Now, okay, so this is kind of preliminary discussion. What I need to do next, that I need to define a function of an operator. So how to do it? How to define this operator? No, first of all, I will explain what needs to be done, but I refer to this very nice book, Functions of Matrices, where this construction is explained in more detail, and also with examples. Okay. So what we are doing? No, first of all, so this construction is based on the famous Mergelian theorem, so which says the following. So given a function with these properties, this function so can be uniformly approximated by polynomials with real coefficients, and this approximation so will be uniform on K. On this domain. So that's very nice. And also, so what is important that so since so we have this property f of z equals f bar of z bar. So for this reason, these polynomials are real. And this polynomial, so if my domain K is disconnected, so still these polynomials are the same for each part, each piece of K. Okay, so if it is so if it is true, so then what we can do? We will do the following. So as a function of L, so f of L is an operator. So what we are going to take just the limit of this polynomial. So we know what is a polynomial of a function or of an operator. Sorry, pk of L makes sense. So pk, it's a polynomial with the real coefficients. So we compute this operator and take then the limit. So it appears that it's a very nice limit. So it exists. It is independent on the choice of this sequence of polynomials, so pk. The result will be an operator, so it will behave as one tensor under coordinate transformations. The result will be smooth, smooth in the sense of x parameter or local coordinates on our manifold, and it follows immediately from the fact that this function, so f of L, if we consider this function as a function of a matrix, it depends analytically. It's the entries of f of L. So these are the analytic functions of the entries of L. So it's indeed the real analytic function in the most natural sense, and also then so this property is also very nice. So what happens to the eigenvalues? The eigenvalues of f of L, so it will be just the f of the eigenvalues of L, and it makes perfect sense because the spectrum of L belongs to this domain K. And so one more property. So since this convergence is uniform, it will follow from this and uniform, and so the result is a holomorphic function. So this implies, so this is a property of holomorphic functions, so that it implies that we also will have convergence of not only of the functions but of the derivatives. So if I differentiate the f of L in terms of Lie derivative, for instance, or in terms of any derivative you want. So if L depends on a certain parameter and I differentiate with respect to this parameter, then so I can just I can compute the derivatives of I can what is it called? I can exchange the taking derivative and the limit. So first I can differentiate these polynomials. I know what this means, and so then take the limit. You can I repeat that. So here you can consider the Lie derivative or the partial derivatives. So it doesn't matter, and hence we immediately we get this conclusion. So if L is a Nijenhuis operator, then the f of L is still Nijenhuis operator. Now, as soon as my function f satisfies the properties mentioned on the previous slide. So why here? No, because the Nijenhuis properties can be written in terms of partial derivatives and L. And since for polynomials, so this is true, then of course the same property will hold for the limit. And that's it. So it is basically this conclusion is based on the properties of analytic functions of matrices, and it is absolutely straightforward. Good. So now what else? Why I say that this is a good idea to consider such functions? So for the following reason, of course, if you take polynomial, you take exponent or sine, so it's good result. But there are much more interesting and useful the analytic functions, and let's consider a couple of examples. So example number one. So we take a characteristic polynomial of my operator L. So you remember that characteristic polynomial is considered as a function on our manifold, so which depends on t as a parameter. Okay, so that is a definition of the characteristic polynomial. So it's almost standard one. Maybe I will always do it in this way: t identity minus L. Traditionally, so this is L minus t identity, but of course so it doesn't matter. No, for some reason I prefer so this definition. And now that let us assume that this characteristic polynomial is factorized into two parts, into two polynomials, chi1 and chi2, like this. I will say that this factorization is admissible if so these polynomials. No, of course, I will assume that the coefficient for the highest or highest power of t equals 1, this partition is non-trivial, but the most important assumption that I will assume that these polynomials have no common roots. It means that I divide the eigenvalues of my operator L into two groups. And one group goes to first factor, and the other group goes to the second factor, and there is no mixture between them. Okay, so then I will say that this the partition is admissible. Next, what I will do, I will consider two distributions. The first distribution, d1, so will be just the kernel of one polynomial, and so the kernel of the other polynomial. From linear algebra, so we know that so these two distributions are these two subspaces are transversal to each other. So like this, they are L invariant with respect to my operator, and also the whole space is just a sum of d1 and d2. I don't know if this construction so seems to be familiar to you. No, but this is that's let me remind you something maybe from linear algebra. So it's one more comment. So if you have an operator, so L, so then what I'm doing. So you know that the space. So if L is a linear operator defined on a vector space V, so then the V can be, this subspace can be presented as a direct sum of the generalized eigenspaces. So V, the lambda I from say from 1 to P. So lambda I is an eigenvalue of this operator. And the decomposition I'm talking about is as follows. As I said, I divide eigenvalues into two groups. That's one group, and some other group P sorry, it's, I have to say, not say S. P plus 1, so lambda S. So like this, I divide all polynomials into two groups, and then I simply say that so the one subspace is I have all these generalized eigenspaces all together in one group. I take the sum I 1 to P F lambda I, and so the other is so just I collect all the others. So V and L I varies from P plus 1 to S. No, just the very natural decomposition into two parts, and so the whole space. So then, so V obviously is the sum of D1 and D2. So that's something very standard. But I rephrased so this the very standard construction in a slightly different way. Good. So now what I want to say next. I want to say the following. So let us consider projectors. P1 is a projector on D1 and P2 is a projector on P2. So my claim is that these two projectors, so these are they depend on the separator L. So I say that in fact this is a function of L. And moreover, so these projectors are not just some functions, but real analytic functions, so satisfying properties that we have just discussed. So why? So let us see. So what is the function? So I need to explain the meaning of this the domain K and function. So this sort of thing. What is that? This function is surprisingly simple. You will see what it is, but I explained this here on my slide. But again, I believe that it's much easier. So if I try to illustrate it with a picture. So what I have again, I have a complex plane. On this complex plane, I have so my eigenvalues. But remember that this factorization I consider. This factorization, I factorize the characteristic polynomial into two real polynomials. So it means that so even if I have a complex eigenvalue, so then so if I have so lambda I, so then that complex the conjugate so will also so it will be present and it will be sitting here. And so here, for instance, that's lambda J, and complex conjugate is lambda J bar. So what I'm trying to illustrate to illustrate the spectrum of my operator. And what I do, you remember, I divide all eigenvalues into two groups, and of course, so those eigenvectors which are complex conjugate to each other, so they belong to the same group. So now I assume that so my first group corresponds to this, for instance, eigenvalues. Yeah, that's one group. So that is so these are roots of the first polynomial chi I, and so these are roots of the second polynomial, so chi2. Okay, so now, so this that is what is written here so in my slide. I take all these eigenvalues, take small neighborhoods. I need these small neighborhoods because my operator depends on x, and in the point I consider, I have some choice of eigenvalues, but now, so if x changes, so these guys eigenvalues, so they slightly change, and for this reason I consider small neighborhoods here. Okay, so now what is my function? My function is very simple. So what I say that my function equals +1 on this part of k, and so 0 on the other part of k. So my function is very easy. It is constant, locally constant function. So that's what I do. So here is my function. For the first part, this is equals 1, and for the other part it is 0. Okay, obviously, so this function satisfies all this property. So it looks like my function is, it's on one part it is 1, on the other part it is 0. It looks like a discontinuous function. No, it is so since it is defined on this domain, which is disconnected, this is a perfect function. So it is real analytic, but defined on a disconnected set. It's fine. All properties are fulfilled. No, and now I simply say that so if I consider this function, if I apply this function to my operator L, so then I will get exactly projector. Because all the blocks which corresponds to these eigenvalues from this yellow the picture on my line. So all these eigenspaces on these eigenspaces, my operator will be just identity because it's +1. +1, it means it's just the operator I obtain will be just identity, and that's it. And for this part, the second part, on these eigenspaces, so this is 0. It means that all eigenspaces from the first group, so nothing happens to them. So this is just identity operator. No, for the others, so this is 0. No, this is projector. This is a projector. Great. Of course, I will do the same for the other subset. I just in my picture I just interchange 0 and 1. Then so I will get the projector to D2. What is my conclusion? So my conclusion is as follows. So if we assume that L, this operator, is Nijenhuis operator, but since P1 and P2 can be treated as real analytic functions of L, then these projectors, they will also be Nijenhuis operators. Okay, that's what is the message? What is the conclusion? So if I consider the complicated the linear operator, if it is Nijenhuis, what I can do, I can consider projectors on eigenspaces I can take just one eigenspace, generalized eigenspace. So this is important, generalized eigenspace. Or I can take a group of eigenspaces together and consider projector on all of them. So this is a good operator, and this is still Nijenhuis operator, which is very simple, much simpler now. One more example of basically of the same kind. Now, let's consider this example we just treated. The function was very, very simple. This function was locally constant, either +1 or -1. So now let's do the following trick. Consider the function which is defined on the complex plane without the real line removed. If z belongs to the upper half plane, my function equals I. And if z belongs to the lower half plane, so my function equals -I. So it's again, this is it's a locally constant function, so satisfying this property. Notice the very nice property of this function. If I square it, so if I consider f squared, then I will get just -1. F squared equals -1. So the f squared is constant, but this function is not constant. F squared is constant, but the function is not. It's locally constant. Good. So now what I say is that this function still satisfy all properties I need. And now, so if I have an operator L such that the eigenvalues of these operators belong to either upper half plane or lower half plane, so none of them is located on the real line. What it means? It means that the eigenvalues of my operator must be all complex numbers, no real numbers, no real eigenvalues. Now then I can apply so this function to this operator, and I will get something. What do I get? So if L now is an operator on the real manifold with no real eigenvalues, so then as we've just discussed, the application of this function, the real analytic function, to this operator, so it gives us an operator J, which satisfies remarkable properties. No, first of all, so J is a smooth operator. So next, so if I square it, so J squared will be minus identity. Why? No, because f squared is -1, but -1 as a function in this on the space of matrices. So the -1, it means it's just this minus identity. That's it. So great. So that's the J squared is minus identity. Also, my operator L and the f of L, so they commute. Operator obviously commutes with any function. Okay. It means that so if I now treat J as the complex structure on each tangent space, so you remember what is a complex structure. Complex structure, it's just on any operator, so satisfying this property. So J is a complex structure on each tangent space. So then L, with respect to this complex structure, so since it commutes with this, so L can be treated as a complex linear operator. That's great. And the most important, of course, the most important conclusion is as follows. So if my L is Nijenhuis, so then it follows from this that so f of this complex structure, it's complex structure on each tangent space. But so if we consider it as an object on my manifold, then it's called almost complex structure. No, but it's not almost. So that's real. This is genuine complex structure. No, for the reason that so if L is Nijenhuis, then J is Nijenhuis. And this is a very famous theorem, Nylander-Nirenberg. I mentioned it in my first lecture. So in this case, so if you have a most complex structure, which is Nijenhuis, so this is just the complex structure in proper sense. You can introduce complex coordinates, and this is that's a very the beautiful result. So as soon as you have a Nijenhuis operator with no real eigenvalues, then immediately you will get canonical complex structure on your manifold. Your manifold automatically turns out to be constant. We will discuss some more corollaries of these constructions a little bit later. So now we switch a little bit the topic, and we will discuss, we will talk about distributions. I have already mentioned here, so this notion, so I said, so we consider two distributions. Now I will remind you some basic facts, basic ideas about distributions, integrability of distributions, and integrals. Okay. Let us consider so the following object. So we have a manifold, and n-dimensional manifold. At each point of this manifold, I consider tangent space, and in this tangent space, I consider subspace. So dx is a subspace of the tangent space point x. I assume that the dimension of this subspace is always the same, so the dimension equals k. And also, I will assume that this subspace smoothly depend on x, smoothly depend on point x. So it varies smoothly with point. Now, then this object is called the distribution. You may think of it also as a kind of sub-bundle of tangent bundle, so if you wish. No, but in elementary terms, it simply means that at each point, so we have a subspace in the tangent space. Let us consider a couple of examples. So the example number one. Let's assume that we have k linearly independent vector fields on our manifold. Then what I can do at each point, I can consider just the subspace generated by these vector fields, these corresponding vectors. So D is just the span of psi1, psi k. It's not very important assumption that they are linearly independent, but I will assume that they are linearly independent. So they form a basis at each point. They form the basis. And what is important, every distribution locally so can be presented in this way. So we can always find locally, so that we can find the basis consisting of smooth vector fields, so which generate this distribution. That is a very standard way. And the second possibility is as follows. Let us consider, let's assume that we have functions, n minus k functions defined on our manifold, and these functions are independent. Independent in the sense that the differentials of these functions are linearly independent at each point. Equivalently, you may say that these functions, if we consider all of them together, they define a map from our manifold to Rn minus k, and this manifold is submersion. Submersion means that at each point, the differential of this map has the maximal rank and equals n minus k. Okay, so now as a distribution, so that I will take just the kernel of the differential of this map. Or that it is the same as to say that I consider fibers for this map. You know what it is. I take a point from Rn minus k, this A, and consider just its preimage. Or it is the same as just to say that I consider common level set for all functions. F1 equals A1, F2 equals A2, so and so on. So then this distribution is nothing else but just a tangent space to fibers. Tangent space to fibers. This distribution is very special. So it's in particular, so we see that so if I consider any vector field, which belongs to this distribution, which is tangent to this distribution, so then these functions f1, fn minus k, so they satisfy this property. If I differentiate this function along this vector field psi, so then that I will get 0. I wrote this derivative in two different ways, as a lead derivative or kind of fusional directional derivatives. It's the same thing. I did it just because some of you may be more comfortable with one or so the other version, but this is the same thing. So this distribution is special because it admits functions size of satisfying this property. Let me again. So what I want to do, that I want to illustrate this with the picture. So the first possibility was as follows. So I consider a point. At this point, I consider two, or maybe more. Xi1 and Xi2. I consider two vectors. I take tangent space spanned by these vectors. I consider another point. These two vector fields will give me something else. And I do it at each point. Xi1, Xi2. That's my first example A. The second example is, so if you look at this picture, it looks like a little bit chaotic, let's say. The second is much more regular, because so I have my space, my manifold, and it is locally affiliated into these fibers. So I have the common the level surfaces.
I'm sorry, but we don't see your paper.
Oh, that's my apologies. Yes, so that's what that's what I was trying to illustrate. Sorry. Please say if I make such a mistake immediately, so let me know. Because okay, so that's you see, this is the first situation, and the B example is as follows. So I have my space, and it is so if we have submersion, so we have some sort of fiber bundle. So there's at least the locally I can think of it in this way, and you see in this case my distribution is much better. So at each point I consider just the tangent space to fiber, so like this. So this picture looks no, I would say much more regular in this case. Okay, and this second case is called so integrable distribution. So we will say that a distribution is integrable if I can find for k-dimensional distribution. So if I can find functions f1, fn minus k, which are independent and such that they satisfy this property. So if I take any vector field which belongs to my distribution, then my functions are constant along these vector fields, and then therefore immediately I will get this picture. So I will see that I have affiliation into common level sets of those surfaces, and my distributions will be like this example B. Okay, so now I think, now I think it's time to make a break. Let's have a break, and then so we'll continue with some more properties of distribution and splitting theory. Do you have any questions?
I have just some question.
Yeah.
Because you said you have from decomposition of the eigensets. Let's say you have K1 and K2, and then you get two distributions, D1 and D2, right?
Yeah.
And my question is how these D1 and D2 are described by like invariant subspaces or generalized eigen subspace of the tangent space, because Lx there, right? L is Tm to Tm, linear operator at each point, and it has it not necessarily have eigen subspace, but generalized, like those cyclic subspace they should have. And so that's my question. How do I see your D1 and D2 from the original L, its eigenspace or cyclic subspace, that kind of point?
But let me try to explain this. It's so you use so this terminology. It's a cyclic subspace. It's perfectly fine, of course. But let me try to explain my viewpoint, my understanding. First of all, we consider, so take an operator. So L is an operator defined on vector space V. Okay. Okay. So then, so what is the generalized so eigen space? So by definition, so it consists of those vectors. So that satisfies the following property. I take L minus lambda identity. So if I apply this operator to V and I get 0, this is called eigenspace. It's V is an eigenvector, and generalized means that's what I will do it several times. I will repeat this application of these operators, okay, time for some K.
Yeah, it corresponds to a Jordan block for the
It corresponds to, yes, it corresponds to Jordan the block, but all Jordan blocks with the related to this eigenvalue. Okay, so it's if you reduce L to the Jordan normal form, so L Jordan. So then, so what you will see, so the following. So say the lambda 1, the lambda 1, 1. So that's one block.
You move your paper up?
Yeah.
Can move your paper a little bit up?
Yeah.
Thanks.
Now, for instance, so imagine that the Jordan normal form for the first eigenvalue, you have so 3 blocks, 3 Jordan blocks. Okay. So then this eigenspace, generalized eigenspace I'm talking about, this generalized eigenspace corresponds to all of them. So this generalized eigenspace is just this one. Yeah. This is so V lambda 1. Okay. Do you agree?
Yes, I certainly agree. And then,
well, and then, ask your question.
You will come up with 2 distributions on M, right? From Nijenhuis operator.
That's right.
And
so now
how it is related with these generalized eigens subspace of L?
What I have explained this. So and by the way, so this is if I consider so L minus lambda I to the power K. So then so what is this? So VL
Can you move
lambda,
your paper up? Please, paper.
Lambda,
I don't see your paper. Sorry, your paper.
Sure.
Okay, thank you.
So this is exactly the kernel of this operator. It's just the same, right? So what I say the following. So now let's consider, let's take all eigenvalues, lambda 1, so lambda 2, say lambda p, lambda p plus 1, so and lambda s. And I divide it into 2 groups. That's the first group and the second group. And then so my D1 will be just the sum of all generalized eigenspaces from the first group. So I take all eigenspaces for these eigenvalues and take the sum. This is D1. And D2, just it's similar. So this is a sum of all eigenspaces for the other group of eigenvalues. P plus 1 to S. That's what I do. In terms of Jordan normal form, that's how I think about this. If I consider Jordan matrix, then it consists of blocks, right? There are many Jordan blocks in this decomposition. And then so what I'm doing, so I say that, so I consider just some blocks and I put them into one part, and so all the other blocks in the other parts. That's what I'm doing. So this is D1 and this is D2.
Oh, I see. Now, how these D1, so these D1, D2 are two distributions on the manifold M, and how they are related with your projection. You said you have another projection. Sounds like projecting to D1, D2.
But let us consider. So let's consider this picture. So you remember what is an operator L? So the L it's in this basis. So this operator consists of Jordan blocks, right? What is P1? P1 is an operator of this kind. So this is identity operator in this block and the zero in this block. And then I consider this correspondence. And in this basis, in the Jordan basis, the projector is very simple. So I replace these Jordan blocks, all these Jordan blocks by identity. And so the other group of Jordan blocks, I replace them by zero. So this is my L, and this is projector.
Okay, but your P1 is considered as a function generated by L, right? So because you need to
you see what this
P1
function. So what this function is, if my eigenvalue belongs to the first group, my function is 1. So if eigenvalue belongs to the second group, my function is 0. And the matrix language, it produces this result. Yeah, it is not maybe not obvious, but there is no cheating here. So it's if you write down this operator in terms of some formulas, you can do it. You can find polynomials which produce this result. It's not obvious. It's not so easy to write down, but it is true. So this correspondence is defined by a nice real analytic function. Okay, so now it's time to continue. Let me continue. So what I want to do next, I want to discuss this topic for distribution. So that I want to remind you the integrability criteria. So how it's given a distribution. So how can we decide if it is integrable or not? This is a famous the Frobenius theorem. Frobenius theorem. So I always think of Frobenius theorem as 2 different versions. So let me give you 2 versions of Frobenius theorem. The first, imagine that we have a distribution generated by k linearly independent vector fields psi1, psi k. I want to decide if this distribution is integrable or not. Frobenius criterion is as follows. You should take a bracket of 2 vector fields, of 2 generators, psi1 and psi and if it happens that the bracket of psi1, psi still belongs to D, so it means that this bracket is a linear combination of psi1, psi k, with certain coefficients, and these coefficients f, I, j, k are not constant, of course, so they will depend on the point. But if it is true, then the distribution is integrable. And of course, the converse is also true. So integrability implies the fact that the bracket of two vector fields will belong to T. So it still belongs to this distribution. So this is the famous Frobenius integrability criterion for the distributions. And the second version of this fact is sort of stronger. So it's the following. So imagine that you have, again, so the same setting. You have k linearly independent vector fields. And so what you want to do, you want to, maybe this it's a very nice result. If you have one vector field which is not zero, you can always find the coordinate system such that this vector field will have coordinates just 1, 0, 0, 0, 0. You can straighten it. So it's every vector field can be trivialized by the appropriate choice of a coordinate system, locally, of course. Can we do it not for one vector field, but for k vector fields simultaneously? So I want to find the coordinate system x1, xn such that my vector field psi I is just the basic vector field. So it has coordinates, components, not just constants, so 0, 0, 0, 1 and 0, 0, 0. Just it means that all of them are trajectories are just straight lines, and these vector fields are kind of the most trivial you can imagine. Can we do it or not? The condition is as follows: these vector fields must commute. It's not like in previous example when the bracket was linear combination. It's more. It's not just linear combination. It must be zero. So if they commute, then you can straighten them simultaneously. You can find the very nice coordinate system so satisfying this property. Okay, I will briefly remind you the proof of both theorems. Proof of theorem 2 first. That stronger result, but it's much easier to prove them. No, first of all, so if vector fields are constant in certain coordinate system, then they commute for obvious reason, because the components are constant and the bracket has something to do with partial derivatives of the components. So since they are constant, so they vanish and the result will be zero. That is clear. I need to check that, so this condition here, that they pairwise commute, this implies the existence of this nice coordinate system. And also, let me immediately to notice this. And of course, this will immediately imply the integrability of the distribution generated by xi1, xij. No, because as integrals, I will take coordinates x, k plus 1, and so on, xn. So they will give me integrals which are independent, and so how many n minus 2. That's exactly what we need. So so this condition obviously implies Frobenius 1. Frobenius 2 implies Frobenius 1. Okay, so now the proof. The proof is based on the notion of the flow generated by a vector field. Maybe again, I will have to illustrate something, to remind you what is a flow and how to deal with this. Flow of vector field. The definition is as follows. Take a point, say P. I I want to say what is phi psi to t of p. So the flow phi psi t, so this is a map from M to itself. Okay, so what happens to point P? So the xi is a vector field, so I take P, so I consider the integral trajectory of my vector field, and so this is a curve. Say here, so P of t here, such that so if I differentiate, if I take velocity vector, so then the velocity vector d by dt, so of t, it's going to be exactly my vector field xi at the point, so P of t. That's an integral curve. Integral curve. And then, so what I need to do, I assume that so P, this my point is P of 0, so this is the initial point, and then now I just shift this point along its integral trajectory by time P. So that's time T, and this is the result. So this is phi xi t of P. So it's each point is shifted along trajectory by time t. So that's how the flow works. Properties. First, how so these things are related. So now if I differentiate the flow with respect to t, that I will get my vector field. No, it's just definition. So if I consider flow by time t plus s, so this is the same as first shift by t and then shift by s. That's also trivial. It means that with respect to t, this family of maps is one parameter group. And so one more property, so if I have two vector fields which commute, so then so their flows commute. No, at least locally, so this is true, and the other way around. So if the flows generated by xi and eta commute, then the vector fields commute. Okay, I will use these properties to construct the coordinate system I'm looking for. And I will do it so in the following way. Again, it's better so if I illustrate what I'm doing. So just illustration. I take a point. So this is my initial point, no say point P. Then so here so there are my vector fields, so xi so 1 and so on, so xi k. I will choose so they generate a certain space here, so I will choose so n here to be submanifold in our manifold, which looks like this, which is transversal to the distribution. So n transversal to the distribution. Okay, so and now so what I want to do, I want to construct a map from so phi capital. So this is going to be a map from R n to my manifold M. Rn I divide into two parts, R k and R n minus k. In Rk, I consider the coordinates x1, xk, and here coordinates y, and that I will do the following. So that I will take point y. So one remark on this on this transversal section, I will consider y as local coordinates. on n. Then so that I will do the following. So that I take a point y, I take on my transversal n point with coordinates y, and then I shift this point along the vector field xi 1 by time x1, then along xi 2 by time x2, well, so and so on. So that's what I'm doing. So now let us look at the level of formulas here. So I take a point x and y, and I take a point y which belongs to n, and now I shift it along my vector fields the different times. So the shift along xi1 by time x1, along xi2 by time x2, so, and so on. So that's what I'm doing. So as a result, I will get a map. So this is smooth map because you know, so this solutions of a system of ODs smoothly depend on initial date and this sort of thing. So this map is smooth, and moreover, it's easy to see that the differential of this map is an isomorphism. Not because you see what happens to the differential, and so basically you will see immediately that the differential is an identity map in coordinates, basically. Okay, good, and so since the differential is an isomorphism, I can treat this map as a local diffeomorphism, and it allows me to identify the neighborhood of my point P in M with the neighborhood of the origin in Rn. My claim is that this coordinate system is exactly the one I'm looking for. In this coordinate system, my vector fields xi1, xik, so they coincide with d by dxi. To get the final result, final conclusions, that I will next just read the note y by x. y1 is xk plus 1, some additional coordinates here. Okay, let's do this computation, and you will see that it follows immediately here. So so what is the basis vector field in my coordinate system? So what I need to do, I need not just to take my map and differentiate, leave all coordinates fixed instead, except for xi, and then the xi I replace by xi plus t and differentiate by t. So this is that's a definition of the basis vector fields. All coordinates are fixed, one is changed, and I take the derivative. Now, but then let's see what happens if I do this derivation. So that's the first formula is here is just it's a definition of my map phi capital. So next, what I'm doing, so that I know that this phi xi plus t, I can represent it as a composition of two shifts. First, I shift by xi and then by t. Okay, so then next I will use the fact that these vector fields commute, and since they commute, it follows from this that the flows commute, and for this reason, I can take this phi xi I t and put it in front of this the expression. So put it here. Okay, It was sitting somewhere in the middle, but I will put it in the first place. So if I look at the rest of this here, so this element, but this is exactly my current point. So phi of tx. So what I'm doing? So I just take this point, I shift it along psi I by t, and then I differentiate. No, but it's a definition of the flow. So if I take the derivative, I will get my vector field, and you are done. So the d by dxi, this is exactly psi I, and that's it. So everything is done. Now I will use so this result to derive the conclusion of the first Frobenius theorem. The first Frobenius theorem, first of all, again, so it's in two ways. In my way, the converse statement is obvious. So if you have integrability, then of course, so these distributions will be closed under the bracket. It's easy. The other way around, in the opposite way. I have k vector fields, psi1, psi k. So they satisfy this condition. So the bracket of any two of them, psi I, psi j, is a linear combination of psi1, psi k. So let's consider a matrix. Matrix, so whose the rows are exactly the components of my vector field. So the first row here. So this is, this is psi1. The second row is psi2, and so on. The last row is psi k. They are linearly independent. So since they are linearly independent, I can assume that so this k by k minor of this matrix is not zero, the first one. Okay, so I assume that the determinant of this block, k by k block, is not zero. So if it is not zero, so then I can find the matrix A such that, so if I multiply A on the left with my matrix B, then so the result that will be as follows. So this k by k block so will transform to the just identity matrix. Now, what is A? A is just the inverse matrix of this non-degenerate block. So A is just the inverse matrix for this k by k minor. Okay, and then what I will do, I will replace psi1, psi k, these generators of my distribution by new vectors. I will replace them by vectors eta1, eta2, eta k, whose the coordinates are just rows of this new matrix. But since we multiply this by A, it means that each eta I new vector is a linear combination of psi's. And this is a change of basis in this distribution. Change of basis with the matrix A. A is a transition matrix. So it is just the basis of the same distribution. I changed this basis, but this property, the fact that the bracket of eta I and eta j is still a linear combination of eta 1, eta k. It's still this property still holds. It's just that I change basis, but the fact that this distribution is closed under the Lie bracket still takes place. So this is true. Now, the funny thing is that if my the components of my vector fields are like this, like shown here, that's 1, 0, 0, 0, and something, and 0, 1, 0, 0. It's some special vectors. It follows from this that this property, that bracket of psi I and psi j is a linear combination of bracket of eta I and eta j is a linear combination of etas. In this special case, it's easy to see that this linear combination is actually 0. That's identically 0. And therefore, we are in the situation of the Frobenius 2 theorem, which, as we discussed, implies Frobenius 1, and that's it. Maybe I need to explain. I need to explain this fact here. So that's a simple computation that maybe let me do it. If I have time, do I have time? Yeah, I have time. I have time. I will do this computation. That what I want to check. So is the following. So if I have two vector fields, so eta, no say eta 1 equals 1, 0, 0, 0, 0, and then some eta k plus 1, eta some coefficients, eta 1k plus 1, and so on. So eta n, it's and eta 2, 0, 1, 0, and eta 2 k plus 1, eta 2 n. So my statement is as follows. So if eta 1, eta 2, the bracket equals, so it's a linear combination. So combination of eta 1, eta k. So then, in fact, eta 1 and eta 2, they commute. So this linear combination is in fact trivial. I will do it in the simplest case, just as an example, and then you will see immediately so why this is true. So I assume that eta 1, no, in dimension 3, say 1, 0, no, some function here, and eta 2 is 0, 1, and some function. In other words, so eta 1 equals dx1 plus f dx3, and eta 2 equals dx2 plus g dx3. Okay, and I compute the bracket. Okay, so let's compute the bracket. Eta 1, eta 2, dx1 plus f dx3, dx2 plus g dx3, the bracket. So I differentiate these guys with respect to dx1. So that's differentiate the first term, it gives 0. The second term, I will get dg dx1 dx3. And I use now this operator again. So the derivative of dx2 gives 0. And here I have plus f dg dx3, so dx3. And now the other way around, I will get minus df dx2 dx3 and minus g df dx3, so dx3. That's what I get. And now you can see immediately that this expression, only dx3 is present here. So this is just some expressions, and so dx3. So there is no dx1, no dx2. So if I assume that this is a linear combination, so it's a linear combination of eta 1 and eta 2, so then it means that this is some constant, some coefficient c1 dx1 plus g dx f, so dx3 plus c2 dx2 plus g dx3, and now let us compare these two expressions. So here there is only dx3, and here we have c1 dx1 plus c2 dx2, and so since these two guys are present, and dx1, dx2, and dx3 are linearly independent from this identity, so we immediately conclude that C1 and C2 are equal to 0. So then we are done. So you see the proof is the reduction from Frobenius 1 to Frobenius 2. And that's a very simple trick. You can always change basis of generators in such a way that they will commute. They will commute, and then everything immediately simplifies. Okay, now let us look at the following property of the image of Nijenhuis operator. Take Nijenhuis operator L. And then to consider the distribution, which is the subspace, which is not just the image of this operator. Okay, but we assume that the rank of this operator is constant and equals to k. The rank drops. It's not n but smaller. So the image is smaller than the whole space. This distribution is integrable. This is it follows immediately from the Frobenius theorem, from Frobenius 2. That's what we need to do. So we need to verify the following. So we take two vector fields, so which belongs to this distribution. This is L psi and L eta, where psi and eta are just arbitrary vector fields. I take two arbitrary vector fields, I take their images. What I need to check? I need to check that the bracket L psi and L eta still belongs to this distribution. So I need to check that this bracket L psi L eta belongs to the image of L. We know the property that L is Nijenhuis, so it means that this Nijenhuis relation holds true. So that's Nijenhuis torsion vanishes. And if I rewrite this relation in a slightly different way, let me see. So what I'm doing. The one term is missing here. So there should be some term here. So let me write it down. The second line, what I need to do, I need to express the bracket of L xi and L eta, and this bracket is going to be not just the L xi L eta equals, and then the second line in this formula, minus L squared xi eta, plus L xi eta, and plus L xi L eta, so like this. So this is that is the second line. And then my formula. I need to check that the result belongs to the image. No, but obviously it does belong to the image because I can just factor out L, and I will see that this is the image of the vector field in brackets. So it does belong. Okay, good. You at this point, it's natural to ask the following question. So let us, if you have a linear operator, you can naturally assign two subspaces to it, the image and the kernel. But we know that the image of this distribution is integrable. What about kernel? So let's consider distribution, which is the kernel of L. Is it integrable or not? The answer is no. It's not always the case. Sometimes, so there are examples of Nijenhuis operators with non-integrable image. And now, so we're ready to prove the splitting theorem. So what I will do is the following. So I will repeat the procedure so we have already discussed in the example one today. I take a point in our manifold. I consider the eigenvalues of my operator at this point. I divide it into two groups. And so this division will give me factorization of the characteristic polynomial into two smaller polynomials, chi1 and chi2. So the first, it will be of the form t minus lambda 1. So I collect all eigenvalues from one group into one polynomial and all the others into the other polynomial. So just a very natural factorization. So now that my statement is as follows. So if I now, this what I do at point P. So if I change this point a little bit, so what happens to this factorization? The eigenvalues, they will change a little bit. They will change, but they still they will change continuously, and for this reason, still, so this factorization lambdas will change, but this factorization still holds true in the neighborhood of point P. Notice also that it doesn't matter for me whether my operator has real or complex eigenvalues. So if it has complex eigenvalues, then I consider real operator. Then the complex eigenvalues, they come in pairs, lambda and lambda bar. And lambda bar should be sent in the same group of roots. So they always come in as a pair, a kind of undivided pair. So there is no mixture. Okay, so I have this factorization. That's admissible factorization in the sense that these polynomials chi1 and chi2 have no common roots. Moreover, so there was an exercise after my lecture 2, the coefficients of these polynomials that will smoothly depend on the point on our manifold. That's a very important thing. The eigenvalues, they are not smooth, not necessarily smooth. But so if I consider the product and open brackets, then the coefficients of polynomials chi1 and chi2 will smoothly depend on the point on our manifold. Okay. And also I want to point out that my point P I consider is absolutely arbitrary point. So some eigenvalues may collide in this point. And so, for instance, it may happen that at this point P, the first eigenvalue has multiplicity, say 4. But then, so if you slightly perturb this point, so these 4 equal roots, they immediately splits into 4 different roots. This may happen. It's not a problem. Still, so this factorization to make sense. So this is important. So P is arbitrary point. So it's absolutely arbitrary. Okay, so now so what I will do, I will consider so the same distributions D1 and D2. And just I collect all eigenvalues from the first group in one part and all eigenvalues, generalized eigenvalues into the other part. Formally, in short, I can simply say that di is the kernel of the polynomial chi I of L. Okay, so we have this the admissible factorization, and so now the conclusion. So this is a splitting theorem. So which says, first of all, that these distributions are both integrable. So they're integrable. So if they're integrable, so then I can find the adapted coordinate system so such that the coordinates x1, x r, so it will give coordinates on the fibers of the first distribution, so the other fibers of the second distribution, or more precisely, D1 will be generated by the first K basis vector fields, and D2 will be generated by the rest, the N minus R, the remaining vector fields. So since these distributions are L invariant, so then the matrix of my operator in this coordinate system so will split into blocks. It will consist of 2 diagonal blocks, L1 and L2. And the point is that this block L1 will only depend on X variables, and this block L2 will only depend on Y variables. So it means that my operator, so as soon as I have the admissible factorization of characteristic polynomial, so my operator immediately splits into 2 smaller operators, so corresponding to chi1 and chi2, and each of which will depend on its own variables. In other words, so this is just L is direct sum of 2 independent operators. And this is it's a very nice fact. Good. Let's prove this result. The proof is easy. We are well prepared to do. Now we consider projectors P1 and P2, and so we know already that these projectors are Nijenhuis operators. And so the distributions we consider, these are simply so images of, so what is P1? P1 is a projector on D1. So D1 is just the image of P1. And so since D1 is image of Nijenhuis operator, the image of a Nijenhuis operator, so is the integrable distributions, we're done. So these distributions are integrable. So then, so what I can do, I can find the adapted coordinate system. So with this property due to Frobenius so integrability theorem, since L is since D1 and D2 are invariant subspaces, my matrix of my operator so will be block diagonal, but it's not the end of the story. I need to show that this block L1 doesn't depend on Y, and similarly so L2 then doesn't depend on X. That's what I need to do. Okay, that I will assume, so for simplicity, that the determinant of my operator is not 0. If it is not true, I slightly change it by just adding or subtracting the identity matrix with the certain factor, and basically nothing changes in my setting. That's no, but that I will get not non-degeneracy. Good. And then let's consider the following operator now. LP1. P1 is a function of L. So if I consider product of two functions, then obviously that is still a function. That in matrix terms, so if I do this projection, so this lambda 2, this block, so simply disappears. Okay, so then this is still Nijenhuis operator. Now, since it is Nijenhuis operator, so then I can compute the Nijenhuis torsion and see what happens. So let's do this computation. So I compute Nijenhuis torsion for operator LP1 by using the second definition with the Lie derivative. So I need to compute here. So this expression here. This expression, I know that the result is 0 because it's a Nijenhuis operator. So now I will do I will take the Lie derivative with respect to the vector field, which is d y alpha. So which belongs to the kernel of, it should be P2 here. So there is a typo here, so sorry. Okay. No, sorry. No. There is no typo. D2 is the image of P2, but this is the kernel of P1. So everything is correct. So it means that so if I apply LP1 to U, I will get 0. It means that the first term in this expression so simply disappears. We end up with the second term. So if I consider now this second term, then that I will get, so what do I get? LP1, no, but this is just this matrix L1, so 0, 0, 0. The second block L2 disappears. The Lie derivative. So since I compute this derivative along just the basis vector field, so this is just a partial derivative. That's partial derivative, so this is the result, and this is 0. Since this is 0, so you see that L1 d L1 by partial derivative by y alpha, then it vanishes, and L1 is non-degenerate. So I conclude that the partial derivative of L1 with respect to by alpha is 0. It means that L1 only depends on x, and we're done. So this is the end of the story. How much time do I have? Almost nothing, but no, still 4 minutes. What I want to do also, that I want to say that this theorem, splitting theorem in Nijenhuis geometry reminds splitting theorem in Poisson geometry, the very famous result known as Weinstein splitting theorem. So this is this theorem so says the following: that if you have a Poisson structure locally, local Poisson manifold, it splits into product of two things: symplectic manifold and the Poisson manifold, so having at the given point of 0 rank. In terms of matrices, it means that locally every the Poisson tensor, the matrix of Poisson tensor, so can be presented exactly like we did in our case, in block diagonal form. So we will have 2 blocks. So one block only depends on x, the other block only depends on y. The first block is non-degenerate. P1 is non-degenerate, so it is symplectic. And P2, it's the other way around. So for P2, at the given point, P2 vanishes. In the neighborhood, it is not, but at the given point, so P2 is just 0. And if you look at this theorem, which is kind of the most important fundamental fact, basic fact in Poisson geometry, so you will see that. So our story, Nijenhuis story, is sort of similar, so reminds of this theorem. And one corollary from splitting theorem, Nijenhuis splitting theorem, so we just proved. But I split this operator into two parts. Then each part can split again into smaller parts and so on and so forth. As a result, that we will get the splitting into smaller components satisfying to the following properties. So if I consider that one component, then at a given point, P, so this component has just one single eigenvalue, or there may be two complex conjugate eigenvalues. So that I can split it, my operator, I can always present it as a direct sum of smaller operators, such that each operator at a given point has either one single real eigenvalue or two complex conjugate eigenvalues. But just I repeat several times. That's my splitting theorem. So then I will get this result. And this is a very important tool. So if you want to study singularities of Nijenhuis operators or study local normal forms, you should start from this. Now, first of all, you reduces the problem to the case when at a given point, not locally, but at just one single point, all eigenvalues are the same. And this is very important. And as usual, at the end of my lecture, I suggest several exercises here, so please pay attention to them. I think the second exercise is very important. In linear algebra, so there is a very nice decomposition of any linear operator into two parts. Semi-simple part and nilpotent part, and it's a so-called Jordan-Chevalier decomposition. Obviously, S and N can be understood as functions of L. Question: these functions, are they real analytic in the sense we discussed or not? So that's a very good question. Okay, and also the last question is important. Just an example of a Nijenhuis operator with non-integrable kernel. So it's a good exercise. Okay, that's all for today. Thank you for your attention. I don't know if you have questions. Still, I could try to answer a couple of them. Short questions.
Well, just a quick short question. So you reduce your L to those irreducible ones, namely those that you cannot decompose any further because it has only a single eigenvalue or a pair of conjugate ones. And then I was kind of curious, how can you write L in better form in these little irreducible blocks? Because there you have still have some coordinates like ix1 to xn, and then you cannot separate them, right? And what is the best form for those irreducible L?
Yeah, good. This is absolutely, yeah. The question you're asking me is this very important, fundamental, and of course, this is one of problems, right, on Nijenhuis geometry to describe the normal forms for these irreducible components. Then, so I can tell you the following. No, the first the assumptions, our additional assumption. Let us assume that L1 of x1 so has a single eigenvalue, not at just one point, but locally in the neighborhood, and just one single eigenvalue. And assume that this L1 of x1 algebraically is conjugate to a Jordan block. Okay, so then there is a nice normal form. So this is a topic of the lecture next week. However, so if so what happens, yeah, so if you assume that at the given point all eigenvalues are the same, but this is just one single Jordan block, not several Jordan blocks, but just one single Jordan block, then again, so there is a very nice normal form. And it is this will be discussed at lecture 10, something in the middle of the course. I will explain this. It's not so easy. It is that it is not obvious. So, but in the most general case, so there is, I'm afraid, no hope to get the reasonable normal form right now. Maybe later. So this is still an open problem. So shortly, in some cases, there are good normal forms, and we will talk about them. In general, it's an open problem.
Thank you. Thank you.
Okay. So then that's all for today. So bye-bye. See you on Thursday.